Okay, guys, this is Professor Floyd, and we are doing OEH 5723 homework set 7, number 3. This is a continuation of number 2, and so we're going to use a lot of the data that we got from that in the structure. So we can see that our hydrogen cyanide concentration was 2.57 to the minus 4 molar when we had our solution buffered at pH 10.8. So I erased the Ka, and I didn't mean to. So let's just start off by first calculating that, and then we'll talk about what the problem here is. Right, 6.1. Okay. So our Ka is 6.166 times 10 minus 10. Alright, so in this problem what we're doing is we're recognizing that even though we made a solution of sodium cyanide, and in the previous problem we ignored the fact that it's in equilibria with hydrogen cyanide. Now we're not ignoring that, and we're recognizing that hydrogen cyanide will partition from the liquid into the gas phase. And this can be bad because hydrogen cyanide is especially toxic, and it's potentially toxic with a lethal concentration of around 120 milligrams per cubic meter. And so what we want to know is, if we were to have a very large vat in a room that was, say, a fairly small room, and it was maintained at 25 C, and the room were to reach equilibria with the headspace concentration, with the partitioning of hydrogen cyanide, do we have a risk of killing people? So this isn't necessarily the most elegant way to decide whether you have a problem or not in industrial hygiene and environmental health, but if you know you're coming close to killing people, then you should probably say we should do something about this. So let's just jump into it. From the previous problem, we determined that our cyanide concentration, based off of putting a kilogram of sodium cyanide into 2,000 liters, was 0.01 molar. Our hydrogen ion concentration came from the fact that we have a pH set at 10 and it's buffered. So 10.8, that comes out to 1.5 or 1.6 times 10 to the minus 11, 1.58. And then our HCN we have right here as 2.57 times 10 to the minus 4 molar. So what we want to do is, we have our hydrogen cyanide concentration, and we want to use our Henry's law, which says the concentration in the aqueous phase is going to be equal to the Henry's constant for that substance multiplied by the pressure of that substance. So pressure is a proxy for concentration, and that's what we're interested in right now. So we're just going to bring our Henry's law constant across and underneath, and we'll be left with our pressure, which will eventually convert to concentration. So on ToxNet, we get a Henry's law constant of our KH is 1.33 times 10 to the minus 4, but the units that ToxNet expresses it in are not exactly the most friendly of units for us. They express it in atmospheres, cubic meters per mole. And we're probably used to seeing this expressed as moles per liter atmosphere. And that's kind of what you classically have it in chemistry and lots of textbooks. And I think NIST is moles per kilogram bar, which is pretty close to moles per liter atmosphere. So what we can do here is we can simply take the inverse of this. This value, the reciprocal, this value will become a large value instead of a small value, and then our units will invert. And so after we do this, we find that our KH is equal to 7,519, and then our units are moles per atmosphere cubic meter. Now we don't need cubic meters, we need liters, and so we would just convert by cubic meter is equal to 1,000 liters. 1,000 liters. And so it'll make this smaller by a factor of 1,000. So 1, 2, 3. So in the end, our modified or our corrected KH is going to be 7.519 moles per liter atmosphere. Okay, so we can calculate this pretty easily. There's nothing very complicated to this. 2.57 times 10 to the minus 4 divided by 7.519. So this is moles per liter, and this is moles per liter atmosphere. So the atmosphere comes up, the moles per liter cancel, and so we're left in pressure units. We have 2.57 e to the minus 4 divided by 7.519. So 3.42 times 10 to the minus 5. And that's atmospheres. So if we divide by 1 atmosphere, then we're unitless. And if we then multiply by 10 to the 6, that gives us ppm. So ppm, or 10 to the 6, that makes that 10, so that's 34 parts per million. So we need to compare against our lethal concentration of 120 milligrams per cubic meter. So we just have to do our industrial hygiene conversion of ppm to milligrams per cubic meter. So we multiply by the molecular weight. And it's important for us to say, what is this that we're dealing with? This is concentration aqueous, but it's concentration of HCN. So it's HCN. So right here, our molecular weight, that's actually the molecular weight for sodium cyanide. So the molecular weight for HCN, of course, HCN, this is 1, 12, and 14, so 26, 7. So roughly 27 grams per mole for our molecular weight. So multiply by 27 grams per mole, divide by the molar volume. This is at normal temperature and pressure, so 24.45 liters per mole. And in this special instance, which I've said a lot of times before, these units cancel and give us milligrams per cubic meter. So, and if we can see, it's basically just going to get a little bit larger. 27 over 25, 24 and a half. So times 27 divided by 24.45, and we're at 37.7. So 38 milligrams per cubic meter. So in this case, are we concerned that do we have the potential to reach a lethal concentration? No, we don't. As an industrial hygienist, should you be concerned about sitting here at roughly a fourth of your lethal concentration? Yes, but maybe you have other controls, maybe you have local exhaust, maybe you have a push-pull over top of this vat, maybe you just have good dilution ventilation. So just because this is the case doesn't mean that you're an immediate hazard. But let's move on to part 2. So part 2, we then say what happens if the pH changes from 10.8 to 10.2. Maybe somebody dropped a little bit of acid. We've looked before and seen that it doesn't take a lot of acid to change the pH. Now this should be pH buffered, but maybe you make a new fresh solution, you've got a new guy, and he doesn't weigh something out correctly, or he doesn't pay a lot of attention. So I'll change my ink color. And let's say now, what if our pH is 10.2? So that's going to change our concentration here. this won't change, but this will change. So pH is the minus log of hydrogen concentration, and that's 10.2. You know, raise this to the minus. You can bring your negative over. Anyways, you guys should be able to do this by now. It's log of H plus concentration equals negative 10.2, and then that is raised to the 10. And that's raised to the 10, which cancels. Alright, so 10.2, our concentration is 1.58 times 10, I did that right. Yeah. It's 6.3 times 10 to the minus 11. So 6.3 times 10 to the minus 11. And so if we do the same thing, we switch these two and solve out for our concentration of HCN, we find that 6.3 10 to the minus 11 multiplied by 0.01, these are all molars, divided by 6.166 times 10 to the minus 10. Unitless gives us a molar concentration of HCN. So this times 0.01 divided by that's 1.02 times 10 to the minus 3. So that is our HCN concentration, 1.02 times 10 to the minus 3. Now we go back to our Henry's law, where our pressure is going to be equal to our concentration aqueous divided by our Henry's law constant. So I keep on erasing this, and I don't know why, but at least I can remember it. So the Henry's law constant with the units adjusted should be 7.519 atmospheres per liter moles per liter atmosphere. And so our concentration is in moles per liter, which is 1.02 times 10 to the minus 3 moles per liter divided by 7.519 moles per liter per atmosphere, if you wish. So we're left with atmospheres. And that divided by 7.519, it's 1.36 times 10 to the minus 4 atmospheres. So again, we divide out by 1 atmosphere and multiply by 10 to the 6, and that gives us ppm. Okay, so times 10 to the 6 to the minus 4, it's just going to move the decimal place over 2. So we have 136 ppm, and we want to get to milligrams per cubic meter. So we multiply by our molecular weight of hydrogen cyanide, 27, and then we divide by our molar volume of 24.45, and this comes out to about 150 milligrams per cubic meter. So now we re-ask that question. Do we have the potential of creating a lethal environment above this vat of sodium cyanide if our pH shifts to 10.2? And obviously the answer is yes, because our concentration is now greater than the lethal concentration of 120. So a small change in pH, or a perceived small change in pH, something that could be accomplished by an inexperienced technician or somebody that's not paying attention or doesn't appreciate the log nature of a pH scale would possibly think that doesn't matter. So the take-home message as an industrial hygienist, environmental health scientist is, yes, you want to be particularly aware if somebody has a cyanide vat, whether it's a metal plating or metal precious metal recovery operation, whatever it is, you want to be aware that they need to keep that as basic as possible and still be able to accomplish their process. Once they start getting into the tens, then you start having appreciable concentrations of hydrogen cyanide partitioning out of the liquid phase into the gas phase, volatilizing. Hydrogen cyanide is particularly toxic, and it can be acutely toxic and kill you immediately, as opposed to being chronically toxic and give you cancer or cause some sort of organ function impairment or damage later. So just a change from 10.8 to 10.2 results in going from, I'm not real comfortable with this as an industrial hygienist, I wish things were better, to, wow, we've got to do something about this. We are at direct risk of potentially killing someone. So keep that in mind. Realize that we're not just doing these exercises for esoteric reasons to see if we can manipulate the equations and figure it out. The bigger picture you should recognize is, do I have this skill under my belt so that I can recognize cyanide is one of those chemicals to be aware of, but what about other chemicals? What about all the other partitioning calculations that we've done? There's a lot to it, and realize that it's important. It's not terribly complicated. This is the sort of thing that as a hygienist you would probably set it up in your spreadsheet, especially if you worked for this facility on a regular basis, and you would just have them check the pH every shift or at the beginning and end of every shift, and you'd pop it into your spreadsheet, and that pH would dictate what the headspace concentration would be, and maybe you'd have control technology reductions based on dilution ventilation or local capture exhaust, and you could predict what the likely exposure concentration would be. So I ramble enough. That's the answer, 150. And is it a problem? Yes, it is.